Hello everyone, I'm back after a year. It took me a while to decide what type of content I wanted to make, but over the summer I decided to sit down and think what subjects I really wanted to cover, and I will plan out the scripts, write everything down, and I'll now present everything to you. And I'll kick this off by proving off the uniqueness theorems of electricity and magnetism. I'll start with the first uniqueness theorem. So essentially, you want to solve the process equation, and it's going to be over some volume, and that volume is uniquely determined if that volume is specified on the boundary of an arbitrary surface S. So suppose you have like two solutions. Okay, two potentials essentially. And I'm going to let another potential V3 equal difference between the first and second potential, the initial two potentials. And thus, I can write the Laplacian, this new potential term, in terms of a linear combination of the Laplacian of the other terms. Which equals 0. And hence, the potentials are equivalent. Now there is a neat corollary to this first uniqueness theorem. So if you have a potential in some volume, it'll be uniquely determined if the charge density is specified and if the value of the volume on all boundaries is specified. Or I mean, the value of the potential on all boundaries is specified. So, a neat little fact. Now, onto the second uniqueness theorem. So, you have some volume which is surrounded by a set of conductors, and those conductors have a particular charge density, rho, and the electric field will be uniquely determined if the total charge on each conductor is provided. So, to begin the proof, I will let two electric fields, arbitrary electric fields, say E1 and E2, they satisfy the condition. The conditions, sorry. And so there will be Gauss's law between conductors. So I can write two equations involving the divergence of these fields. Yeah. Hopefully my handwriting is readable. Okay. So this is of course going to be equal to the charge density over the permittivity of free space. And then I have the second equation, or the second electric field, which is equal to the charge density over the permittivity of free space. And I can write the electric field over the outer boundary, or I can write an integral representation for the electric field over the outer boundary. So I'll have two surface integrals, and that's just the total enclosed charge or the permittivity of free space. And I can do this again for the second electric field. And just like with the first uniqueness theorem, I'll define another electric field. I will let E3 equal the difference between the first two provided in the proof, which would then imply the divergence equals, the divergence will vanish. And so this implies that the surface integral over this third electric field will also vanish. And that essentially concludes the proof for the uniqueness theorems. Sorry, I forgot one part of the first proof. The second proof is entirely complete. However, for the first uniqueness theorem, I only considered half the proof, where the charge density was non-existent. Now I'm gonna consider a non-zero charge density. So now let's consider. That's why the PDEs both vanished in the first case. Now I'm considering a case where they don't necessarily vanish. And so essentially now you have a Poisson's equation instead of Laplace's equation. Okay. Okay. Now I'm going to take second PDE. It's still fairly simple. It's very straightforward, but this is the actual way to conclude the proof. I have to consider both cases. One where the charge density is 0 and one where the charge density is non-zero. Right, so I have the difference in the Laplacians, and that gives me negative rho over epsilon sub naught plus rho over epsilon sub naught. That equals 0, which implies V1 equals V2, and this actually completes the proof to the first uniqueness theorem.